Okay, today's lesson is on 2D momentum problems. So we are beginning. I have everybody in class currently working on this bell ringer. So you're going to hear a lot of silence right now while they work on it, but you should pause the video and do the bell ringer. Oh, no, not that one. That's not even the right one. That would be very bad. Okay. Yeah, no. Yeah, this one. So the velocity of Jim Bob, 6 meters per second at negative 20 degrees down in the fourth quadrant. Has a mass of 50 kilograms. He collides with another hobo, that's Horace, by the way. Horace, the X is silent, who has a velocity of 4 meters per second at 60 degrees and a mass of 100 kilograms. What is the total momentum of the two? As I just told them in class, essentially you're just doing a vector addition of two momentum vectors. Not from space. You already have it done. Let me help you guys a little bit with what I'm looking around just briefly and seeing a problem with, and that is I think some people are struggling potentially with what the heck these angles mean. You are used to me drawing pictures in this class from a side view. Okay? You do a force diagram of a car, you're typically used to the side view. As we head into the end of this chapter, and definitely the next one, there are two other major perspectives that are certainly going to help us out quite a bit. Okay, one of them is a top-down view of that same car. Okay, top-down view. Okay, the other is going to be the back view of the car. Now, why would we need to look at these other perspectives? Why haven't we so far? Well, we haven't so far because we haven't, mostly the forces, we could see everything we need to see all of that looking at the side. But let's take the collision between Horace and Jim Bob. Are there forces acting up and down on them? Sure, but what are we probably going to assume about force normal and force gravity on them? We're regularly going to cancel, and they're not really going to come at play. Which perspective are we probably looking at this particular collision in? Top-down view. So when I give you these angles, okay, when I give you these angles, what you want to think is this. Imagine the two hobos are out in some type of field, and I'll start with one. Okay, let's go with, I think Jim Bob was first. He's at negative 20. All that means is respect to the field, he's headed that direction right there. There's the momentum of Jim Bob initial. There's your original vector. Okay, where does Horace have to be in order to collide with him if he's going to travel at 60 degrees? Like upper left, top right, bottom right. Where is he going to have to be? If he wants to go at 60 degrees and collide with Jim Bob, where is he originally? He's probably on the bottom left already. He's right down here, so that he can go at 60 degrees to collide with Jim Bob. Does that make sense? So these are your two momentums. All I'm asking you to do is take these two momentums, should be a little bit larger by the way, and do a vector addition. So if you want, imagine I just gave you these two vectors and asked you to add them. That's it. That's it. Going all the way back, super easy peasy stuff from chapter 3. See what you got. If you're struggling and need help, here's the basics of vector addition real quick. Split both of them into the x and their y's using cosine and sine. Add all their x's, add all their y's, and then combine them back together again with Pythagorean theorem and inverse tangent. Don't forget that your calculator screws up quadrants 2 and 3. Well, maybe. Hold on. It was 300 at negative 20, right? And 460, right? No. You can't add the velocities. You add the momentum. No, but you can't. You did. I think you did a vector addition. Yeah, you did a vector addition with the velocities and then tried to put the mass to it. You can't do that. You can't. There is no conservation of velocity.
No, what I did, I multiplied the degree and the velocity, not the mass.
Yeah. There. I'm rounding here, but so you can check to see if you have the right answer. The correct answer at the end should be 540 at 27 degrees. 540 kilogram meters per second. All right, there's your work on the page. Questions, concerns there? One shortcut that you saw me take that I would highly suggest if you haven't yet already incorporated it that I would do is I've divided vector addition up into 3 steps. Split them all up into their x and y's. Add them all up and then put them together in Pythagorean theorem at the end. One thing you'll notice that I did is I just take the first two steps and combine them together at the exact same time. I'm adding up the total sum while finding this individual x, while finding this individual x. The nice thing about doing it that way too is if you do it correctly, to get the y equation is literally just the exact same equation. The only thing you have to change is the trig function from cosine to sine. Questions, concerns here? Yes, Keiser.
So whenever we draw like the vector addition, because I know you had us do that, since it doesn't specify like where they start, can we just like do it without the graph and then just show like their momentums going to each other?
Let me show you the two different ways that you draw it. And I'm fine with either, but both, you definitely need to be able to do both. There's not just one way to get comfortable with and just do it. So for starters, the first way to do it, I have already drawn. It's this.
Yeah.
There's the two momentum vectors. Okay? Now, this makes the most sense for the collision, but it doesn't necessarily make the most sense for understanding, like I said, the vector addition of what you are doing. So you should be able to do both. Yes, you should draw this. I would highly suggest you draw this. But the other way you want to draw this that changes is taking this vector, the momentum of Jim Bob initial, and drawing the next vector on the end of the first one. And now your answer makes sense. Now that the total initial, okay, is up at 27 degrees and 540, and that arrow makes a lot more sense. There was a question, Chloe, do you still have it or no?
No.
Okay, fair enough. So, do we understand what we just did here? It's important because it gets a lot more complicated beyond this. I think that last hour seemed like looking at faces wise. If I was just well, you know what? Let's not judge faces. Give me a 1 to 5 your comfort level with doing just this vector addition. Pretty high numbers around the board. Okay, it's a Friday. We're feeling bad. That's what I'm looking at. Great. Okay, awesome. So, how does this incorporate momentum? Well, let's start off with the easiest thing first. What we are looking at right here is what you're already doing. Conservation of momentum. We are just going to continue conservation of momentum. Now, this appears to be the equation for conservation of momentum in one dimension. But you'll remember that momentum, very importantly, is a vector. Yes? What you would usually do right now, if this was the problem, is you would say, okay, what are the total initial momentums? Where they'd be the momentum of Jim Bob initial plus the momentum of Horace initial. Now, the last two depends on what type of collision this is. Let's keep it easy to begin with and think of this as perfectly inelastic. What are Jim Bob and Horace going to do if this is a perfectly inelastic collision? They're going to stick together. This is going to look like, not very accurate, but a ridiculous Acme style, like you remember like when cartoons, when they used to go into this thing and it became that big cloud and like the head would stick out. And essentially that going in one direction. Now, which way should they end up after colliding? If that's the case, due to conservation of momentum, they should be headed in this direction. Why? Because the total initial momentum has to equal the total final momentum. That arrow, so what you've been doing one-dimensionally is, hey, if I have an end with a total of 10 kilogram meters per second, what's got to happen at the end over here? It's got to be 10 kilogram meters per second. Initial and final have to match. Yes, that's what we've been doing essentially. It's the same thing, except now this arrow has to equal that arrow. So not only does it have to be the same size, but it has to be the same direction. Now, if this is perfectly inelastic, then the final is just all of them added up. Yes? And I would ask a pretty easy question out of this. I would say, what is the velocity of Jim Bob and Horace at the very end of this? Now, keep in mind, you cannot add velocities. You cannot vectorally add velocities. It doesn't work. You can only vectorally add momentums. But once we have already done that, this is here, this is here, this Actually, I should say the adding of these two gives us that. And that has to equal the total momentum final. So what simple thing, so this right here is 540 kilograms meters per second at 27 degrees, yes? That's the total momentum initial, which has to be the total momentum final. If that's the total momentum final, what simple thing could I do to get the velocity of m at the end? Yeah, that's it. Essentially, if the total momentum would equal the mass total times velocity final, right? So velocity final would equal the momentum total final divided by mass total, just some basic algebra over here. Or 540 kilograms meters per second at 27 degrees divided by 150. What do you get? 3.6, almost. There it is. Meters per second at 27 degrees. How are we feeling so far? Easy peasy? Because it gets worse. So I want to make sure you're good. Okay, just assuming it's a gloomy Friday. I get gloomy Fridays suck. Okay, that's what I'm looking at right now. All right, so let's go on then. Let's make it a little bit more interesting. Let's say, switching colors, been using a lot of pink, we have an intersection. Okay? And let's do this. Down here we have a Jeep Wrangler. The mass of the Jeep Wrangler is 1,800 kilograms. Jeep Wrangler is traveling up, not very quickly. Well, you tell me a speed, I don't care. 20 meters a second. So it's about 45 miles an hour. I like it. Velocity of the Wrangler initial is, oops, sorry, you said 20. 20 meters a second. And according to my picture, what angle did I draw it? 90 degrees. Now in this lane, it's a tiny little Prius. Now I say tiny, but I looked it up. They actually are a decent size. I have not. Mass of the Prius is about 1150. Okay? I want to say this tiny little thing is booking it. So how fast are they going? 40. Okay. Yeah, I like it. Let's actually go a little faster. Let's go 60. I say a little faster. 60 meters per second is roughly how fast?
120.
If you double it, yeah, but then you add the other quarter on top of that. This is like 130, 140 miles an hour. They're booking it real hard. Yeah. And what angle would this be at? 0 degrees. Now, by the way, the arrows I'm drawing for the sake of understanding are certainly going to be velocity arrows that I'm trying to draw right now, not momentum arrows, because those can potentially change a little bit. But I don't think they actually change very much. So this is the velocity of the Prius, and this is the velocity of the Wrangler. Now, they're going to collide right here in the middle. Okay? Good news, bad news about this chapter. The good news is the math is just vector addition. Okay? That's it. The other good news is I'm going to heavily encourage you in difficult situations such as the one that I'm about to do to essentially pretend and play with cars. Okay? If you remember being a little kid and representing the Prius as apparently this Lambo right here, and the Wrangler is apparently this NASA semi-truck, because I don't have either of those two toys in the back. I'm going to be going, and I'm going to ask that you try to predict correctly which way these things should probably go. After colliding and hitting one another, who knows whose fault it is? Okay, probably the Prius people. Anyway, which direction would you guess the Prius is going to end up? Like, give me a quadrant, give me roughly an angle. Remember, they're going to play. Here we go. Here's, yeah, just play your toys here. Okay, right here. Okay.
Prius is gonna go like 30.
30?
Wait, not 30, like
27.
15.
You think it's gonna go like this way?
No.
So the
It's
Prius,
going really fast.
so the Prius is going here, and then it's gonna collide, and it's barely gonna change its direction. Keep in mind the Prius is like tiny compared. I mean, it's almost
It's
1 to 2
fast.
here.
Fast.
I don't care how fast it is. It's tiny. Who's gonna change direction more?
Prius.
If I run into a sumo wrestler, okay, this is a sumo wrestler, and this is Spainhour. Who is gonna change direction a lot more? Me. Meaning, if the Wrangler's at 90 and I'm at 0, out of the 45, I'm guessing I'm going a lot more this way than he is going the other. Does that make sense? Okay, who's gonna change direction the most? All right, I don't care. You pick which way you want it to go. You said the Prius is which way?
27 degrees.
That bothers me so much, but all right, fine, whatever.
You asked.
No, it's not. I know it's not accurate. Actually, I'll show you why I know later.
70
40.
62.
Hold on. I'm trying to remember my numbers from earlier. Hold on. I want to make sure. I don't want to end up. I don't do a crap ton of work that you're about to see, and then get to the end and be like, "And this doesn't make sense," and this is why it doesn't make sense, because this is hard enough as it is. So let me try to remember. What was our end result? Our end result is back here.
It's cheating.
63.
Are you looking at the previous hour? Sure. All right,
You
fine.
use pink
Looking at
for
the
this?
answer.
I'm looking at the answers. There it is.
There's-
Yes. Okay, I'm at 27's fine. 27's fine. I don't like it, but it's fine. Now, oops, I'm not on the right one at all. Why are you not moving? Stop being slower than me. Okay, here we go. All right, so you want the Prius at 27 degrees. I'm sorry, last hour, if you're listening to this. I'm going to change colors for what happens after the collision. Pick a color.
Yellow.
Blue. Pink.
We used pink already today.
Orange.
Orange it is. Orange it is. Okay. So the Prius is going to end up then roughly here. Momentum of the Prius. And it would slow down, but probably not a ton. So I'm going to say they're now at 40 meters a second at 27 degrees. Here's the question I have for you and your group then. Okay? Make a prediction. Where should the Wrangler probably go? Which way should the Wrangler be going, and roughly are they going fast or slow after this particular collision? Okay, so discuss in your group based on the results. Again, you got Prius coming in this way. Okay, if it helps to have actual cars here. Prius is coming in this way. Okay, Wrangler is going here. Wrangler's not moving very fast relative to the Prius, like 1/3, but is bigger. Okay, so here it is. They collide, and you've just told me the Prius is going to go this way. The question that your group has is, where should the Wrangler go? Go, discuss. Try to give me roughly a quadrant and definitely about a rough angle.
Where's the Prius hitting the Wrangler?
We don't know. We don't know, because you're right. That does affect things. You're not wrong. You're 100% right that where it hits does affect things. All you're looking at right now is like, imagine you watched this happen and something's blocking you from looking at the Wrangler. Okay, so you just see them. They see the Wrangler come in. You see the Prius hit. You see the Prius take off in this direction. Just from the results, you should be able to tell me roughly where the Wrangler should be going. Let's start off basically and make sure everybody's roughly in the right area. What quadrant should the Wrangler be moving in?
1.
No. 4.
1.
Yeah.
I told you 27 was a little dumb. I would have expected, if it were me, I would have expected a lot more of this. But
Oh, it's just like negative.
I would say the Wrangler should probably end up, if I'm not mistaken, somewhere down here and not moving very quickly. All right. Yes. Abby.
How are we allowed to pick the angles again? Like when you have the initial momentum, isn't your path set?
Excellent question. Yes and no. What Chloe said a minute ago about where they strike each other has a big impact on actually what direction they head in. If we just assume that, for example, right here, okay, if we assume that they just kind of hit on the corner evenly, they're kind of hitting that way, you kind of expect them to go evenly. But for example, if you imagine that the Prius kind of came in first and collided, you'd expect the Prius to go a lot more this way than you would have otherwise, or vice versa. If you expect the Prius to hit into the side, you'd expect this to go. So the direction can kind of change depending on where they would hit. There is a way to calculate exactly what angle it is. It ends up being an extraordinarily messy 4-equation, 4-unknown problem, as this concept is already challenging. Hopefully we're seeing, I'm trying to keep it kind of within the realm. So I am picking what the speed is at the end, and basically the answer to this, or what I'm asking you in this question, or what you're going to be asked on the homework is like, hey, basically this entire same setup. But the question on the table is, what is the velocity of the Wrangler at the end? So all I'm asking you, of course, to do right now is just predict what you think it is, and let's see if that actually matches what's going to happen in real life. All right. So how do we do this? Okay. Well, it's a very, very similar setup, and I'm going to ask you to do it the long way first because the long way makes more sense, and it will still be a struggle. Okay. I will show you the short way for some of you that feel like you understand this a little bit better towards the end. But let's start right here. And the first thing I'm going to ask you to do is real basic, just the same thing that you did on the beginning. I want you to find the total initial momentum, just like you did with Jim Bob and Horace. You have the initial mass, the mass, not the initial mass. You have the initial velocity, so you can get this momentum. Okay? You have this mass and this velocity. Also, I'm going to help you out with something real quick here. Okay, if I take 1150 times 60, I'm going to get a big number that I don't want to write a bunch of zeros this entire time because it's going to be messy. It ends up being 69,000. So to keep this as simple as possible, the answer to the initial momentum of the Prius is 69,000 kilogram meters per second. So to make my life easier, I'm going to say this is 69 kilograms meters per second. So I can write less numbers for this pretty much it. Okay, I want to write 69 instead of writing 69,000 every time because then I have to write a bunch of zeros and it's going to take a lot of time. Same thing over here. So 1800 times 20. It's going to have this 36,000. So I'm going to write that the velocity of the Wrangler, sorry, not the velocity. And I screwed up over here too. My apologies in case you were curious about that. Yep, screwed up. This was the momentum of the Prius initial. And this is the momentum of the Wrangler initial. Should be 36 kilograms meters per second. To wit, someone should say, shouldn't you just say megagrams? Yeah, I probably should, but I'm not going to worry about that right now. 100%. Scientific notation, though. This is scientific notation. Whenever you write kilo just means 1 times 10 to the third. So like I said, I should just say mega, but we're not worried about that right now. We're not worrying about the numbers at all. We're worrying about the concepts, making sure you understand what the heck it is that's going on in a limited period of time. So all you're doing right now is taking 69 kilograms meters per second at 0 degrees plus 36 kilograms meters per second at 90 degrees. And what is that total? to. Oh shoot, that's really bad. Okay, we'll change that. You really don't want to do this. I'm going to change the angle of the Prius because it's going to be bothersome real quick. I used numbers from last hour. I forgot that I asked them for their own numbers, so their numbers are different. Okay, where are we at? Good morning, sir. Well, if I've got coffee from you, what's your name? Antoine. Pleasure. Let me get you. Alright, let me get you a.
No, I don't do it. I don't do it no more. I work at the road for them.
Hey,
I couldn't go today because I meeting. Not Tuesday. But I went yesterday.
let me get you your money, alright? I don't know if anybody's ever put two and two together, but I really appreciate you guys buying protractors. Here you go. Your protractor supports my coffee habit. Why?
I gave up Starbucks this month, so you should give up coffee.
So you're doing a thing.
So you should.
So I should do a thing.
You have an
Addiction? You're frustrated.
I drink about
Yeah.
1 cup a day, unless
Oh,
I
that's
order
not
from
bad.
them, in which case I order 2 cups a day. So I think I'm okay. And actually, on the
That's
weekends, I
not
try
so
not to drink coffee at all. So.
That's not near
What's your favorite type of coffee?
Black.
juicing it.
Black. I go to Starbucks and they get mad at me because I'm that person. I like coffee. You go, I said, just go to the thing, pour. Just pour in a cup and give it to me. I don't need. If it takes more than the words coffee out of my mouth, I don't want it. All right. So you're hopefully seeing why it's a really bad idea if we put the Prius at 27 degrees, because together collectively, if they combined together, it'd be 27.6 degrees. So let's at least make it higher than that. Let's go ahead and call it let's say 40, or let's go 50 degrees. How's that sound? Is that reasonable? Keezer, you were the one pushing for 27 hard. You cool with 40? Can I change it? Never mind, you're not even paying attention. All right. After it collides, we're going to say it's 40 meters per second at 50 degrees. Why do you care so much? Yes, Chloe.
Okay, so whatever you're doing, how did you get the angle?
Which
Like
one?
the result.
The resultant? We're just doing vector addition. So add all the x's, add all the y's, which is easy because it is just an x and one y, right? Once you have the total x and total y, how do you get the magnitude? Let me help you with this. Correct. So these two right here, really, this is what I was talking about with Keezer a second ago with the Horace and Jim Bob example. Draw this so you understand what's going on. Absolutely. But then draw this. Here's the momentum of the Prius initial and the momentum of the Wrangler initial. So how did you get that? You did Pythagorean theorem. So to answer your question, how do you get the angle? Specifically, inverse tangent. Yeah. Okay. Is that not your question, or were we? Oh, no.
I meant like.
The Prius one?
What?
Ask your question. I'm stopping you way too soon. I apologize.
So like I have everything. I just don't know. Like when you do draw your triangle, I don't know which angle to use.
Sure.
for
Okay.
the
Technically, either angle usually works. We regularly, when doing vector addition, always kept our angles with the x-axis just to be consistent. You found this though when we talked about work last chapter, okay? Especially in forces. You're gonna get some different angles. Both of them are fine. To say that this is from the horizontal 27.6 degrees is to say that that angle up there is 52.4, right? They're the same thing. It means the same thing. All you would have to do is remember when you go back to angle, if I just write angle, don't forget that there's an assumption that that's from the x. That's why I always go to the x, because everybody's assuming if I write 27.6 that it's from the x and I don't have to write extra stuff. But if you wanted to write extra stuff, feel free to write 52.4 from the y-axis, and that is literally the exact same thing. Does that make sense?
Yeah.
Cool beans. All right, next. So, what do we know about, what do we know this does? Let's go to another page here real quick. Oh, no. Please tell me. No, I need, do not cancel out. I'm going to be very irritated. A lot of times when I press this, it closes out the program. I don't want to close the program. Please close. This is not good. Sorry, everybody. Oh, good. Oh, okay. We didn't lose. I was afraid we could lose the recording. Darn it. Technology freaking getting in the way. Here, hide. You have no idea how badly that hurt.
Yeah, no, this happens in lab like literally every day.
This is what you're finding this for.
Oh, yeah, you're right. I just wrote the
Okay, it's a giant board now. I don't have other pages. Fair enough. Continuing on. So, if we do the math, here's what it usually looks like. Sum of momentum initial equals sum of momentum final. Yes?
Yes.
Okay. So we would, in this example, have the momentum of the Prius initial plus the momentum of the Wrangler initial is equal to the momentum of the Prius final plus the momentum of the Wrangler final. The question on the table is, what's the velocity of the Wrangler at the end? Where is that buried inside of? We need this. I told you a minute ago that I'm having you do this the long way, and I promised to show you the short way at the end. Here's what I did because we're not quite done, and I'm going to make you take a whole other step in this that you don't usually have to do. But here it is. Here's what I just made you do. You just combined these two together. Okay? By combining those together, you have the total momentum initial, right? Essentially, actually, I didn't need to erase that because essentially what you have done is you have found this, right? Now, what I showed you at the very beginning problem with Horace is that this initial momentum is equal to the final momentum. Pictorially, here's what I'm saying. You took the momentum of Prius initial plus the momentum of Wrangler initial, and you found, switching colors, the total momentum initial. That equation at the top says that that arrow, that vector, must be the exact same as the final. So now, if I switch back to the color representing the individual momentums, this is why I said the weird thing with the Prius. If the Prius is at 50 degrees, then it's going to make a momentum that looks like this. The momentum of the Prius final, right? And in order to conserve momentum, the Wrangler has to have a momentum that looks like this. AKA, if the Prius bounces off at 50 degrees, we should expect the Wrangler to be going down here into the fourth quadrant. If the Prius goes off at 50 degrees, we should be expecting the Wrangler to go down into the fourth quadrant. How are we doing here? If you can get this, this is your momentum diagrams for these. These two momentums must add together to get this momentum. which is equal to this momentum, which must be a combination of those two momentums. Yes? Yes.
Kinda lost. Is that why you said you didn't want to use 27?
Yes, I said I didn't want to use 27 because the total of this was 27.6, which would have meant the Prius is weirdly it collided and goes that way, which means weirdly the Wrangler would have to be going up, which does not make any sort of level of sense whatsoever. I'm trying to match what would actually.
It gets hit like the back.
100% it could. 100% it could. And it's possible. I'm trying to put a picture together of something that would probably make the most logical sense of a collision, like if you were a little kid and driving your vehicles and going that type of thing. But you're right. You are not wrong. It is 100% within the realm of possibility. Okay. So the question on the table now is: you just did this. This answer right here is that number right there, right? And therefore, it is also that number right there. So the question is, what do we do now to figure out this? Okay.
Vector.
Well, yes, but what's that? Do we have the angle of which one? The Wrangler? No, we don't. So, well, I'm going to get you here. I promise. Let's say I go to this equation again. The momentum of Prius initial plus the momentum of Wrangler initial equals the momentum of Prius final plus the momentum of Wrangler final. If I just asked you in simple basic form, just let's say this is one dimensional, what do you do to isolate the Wrangler final? Yep, you do.
You subtract.
So you're going to take the momentum. Actually, you know what? We combined these together already. So I'm going to combine this. This is not just individually. This is the total momentum initial, which is what you know, is equal to the total momentum final plus the Wrangler final. So I just subtract that on both sides to get this right here. Now here's what I just said. Looking at the final triangle right here. Is everybody comfortable with this? So what I said was, if you take the final, which is equal to the initial through conservation of momentum, okay? All I have to do is subtract a vector. How do you subtract a vector? Correct. If this is A, how do you get negative A? So the size is exactly the same. What's the only thing you have to change? The direction by adding or subtracting 180. So we said that the velocity of the Prius afterwards was 40 meters per second at 50. So the momentum, sorry, that should be velocity there. The momentum of the Prius final should be, somebody calculate that for me. 40 times 1150.
Oh.
Where did I get 1150 from? Mass the Prius. That hasn't changed. So this is 46,000 or 46 kilograms meters per second. I should have just used some nicer numbers so I didn't have to do this. But at what angle?
50 degrees.
So how do I make that vector a negative vector? So it's 46 kilogram meters per second at negative 130. Or if you prefer 230 for the same thing. So now you're going to take this vector right here and add 46 kilograms at negative 130 degrees. And that will be your what? That'll be your momentum of the Wrangler final. Once you have the momentum of the Wrangler final, what simple thing can you do to get the velocity of the Wrangler final? Take that number and divide by its mass.
So, is this assuming that on the problems of the homework, can you tell us like the velocity?
Yeah, I would tell you the velocity of the Prius at the end. I would already tell you those numbers. So you would know the velocity, both masses. You'd know the velocity of the you know the velocity initial of both of them, and you know the velocity final of one of them. Now, that might seem like a lot, and how would we know that, except if you look back at your one-dimensional problems, also already what I do. The only difference is, instead of telling you angles in the form of 27, 90, or 0, I tell you direction as this one's going right, this one's going left. It ends up going right, which is just 0, 180. 0, 180, which you rectify with 0 and negative. Sorry, positive and negative. All right. So, okay, Spainhour, let's go back to the beginning. What the heck? How do I do this problem? How do I start it from scratch at the very beginning? Tell me what it is I'm supposed to do. I told you the long way of doing this ahead of time. And the reason, and we're not going to actually here, I'll finish the problem for you real quick, because I don't want to ask you to do another vector addition and take up a little bit more of our time. But let's see here. Help me out real quick. What was momentum of Prius initial? 69 at 0 degrees, right? Yeah. And 36 was the Wrangler, right? Yeah. Okay. And we just said that Prius final is 46?
Yeah.
Okay. That's funny. Okay, so the final answer here is, and this sort of makes sense. The final answer here is 39 kilograms meters per second at 1 degree. So what's going to happen, I was a little wrong. I told you that it was going to go down to the 4th quadrant. The car is actually going to end up going this way. Which makes sense because the total is right here. So if the total is right here, the Prius goes that way. Actually, the total is right here. Total's right here. Prius goes that way. Kind of makes sense that the Wrangler would go this way in that particular case. Here's what you're doing on the problem. How did you? All right, go up there. You came back. What you're going to get is a problem like this, and essentially I would suggest you start right here. I'll hustle real quick. Hold on. To get this, all it says is take this vector and this vector, which you added together, and subtract that vector. So to get the final answer, you take the initial of the Wrangler plus the initial of the Prius minus the Prius final to get the Wrangler. Or in other words, you have these vectors. You have, shoot, why am I struggling with that one so hard? 69 at 0 degrees, 36 at 90 degrees, and 46 at negative 130. If you take those 3 vectors and add them together, that will get you this right here. That's what this math says. This math says add those 3 vectors to get that guy right there.
Can I take a picture? That makes